Hello everyone, my name is Alman Dilis, a software engineering student here at Makerere University, and today I'm going to be taking you through our project, which is a light vision model-driven real-time audience perception support for counselors and therapies. So some of the keywords which I'm going to talk about are micro-expressions, light vision models, knowledge graph-based reasoning, real-time explainable feedback, affective computing in clinical settings. Let's go to next page. This is the content of my presentation, the introduction, related work, problem statement, research questions, and objectives. So let me start off with the keywords. So micro expressions, these are the brief involuntary facial expressions revealing true emotions. These are the expressions which last less than a microsecond or less than a second actually. But the beauty with them is that they contain the true emotional or internal state of a human being. Light vision models, these are the deep learning models. It is a deep learning model or simply a branch of AI which trains on massive image data set. It is able to learn, let's say, a given pattern from those images and then produce an output or interpret the visual data. It's okay. We actually feed it with images and then it is able to give us the output or the interpretation of those images. Knowledge graph-based reasoning. This is a structured network of interconnected concepts. We are using graphs to map the relationships between emotions and behaviors, between the micro expressions and then behaviors, and also clinical states and therapeutic activities. Real-time explainable feedback. This is providing feedback using our AI during the session and showing why certain states or suggestions are detected so that therapists can understand and trust the model's reasoning. Affective computing in clinical settings. This is a technology that recognizes, interprets, and responds to human emotions using sensors, speech, and facial data, which is applied in therapy to understand clients' emotional states and reactions. Um, this is some of the related works to our model. But let me explain or talk briefly about our model. This model, this AI system, is a model that helps therapists and counselors to detect nonverbal cues, which are often missed during the counseling and therapy sessions. So when we detect these micro expressions, we are able to know the real internal state of a client so that we can come up with better ways of handling them. For example, if we notify the therapist that the client, the disengagement, the client is disengaging, or the client is depressed, or the client is anxious, what do we expect the therapist to do? The therapist might maybe pause and then ask more questions on a given topic. So the domain application problem. Therapists need real-time objective support to interpret clients' nonverbal behaviors. So the facial expressions, we really need this system because it is lacking, and that's why we are having a fallout with the counseling and therapy sessions. And then the computational problem is that we want to develop a transformer-based system that analyzes micro-expressions, body language, and gaze in real time, then performs knowledge graph reasoning and delivers explainable feedback on client engagement and affect. The objectives and the questions to develop a fine-tuned vision transformer model for micro-expression classification, construct a research-backed therapy knowledge graph, design a knowledge graph vision language model architecture for clinical decision support, and then deploy and optimize real-time inference system. But what deployment strategies enable efficient inference on the edge devices? And we're going to look at how we can effectively fuse visual embeddings with graph reasoning for therapy recommendations. So what we have already done is that we have developed the AI-based model for counseling and therapy support. We built data sets on facial expressions and behaviors, emotions, clinical states, and interventions. We deployed a light vision model-driven real-time audience perception support for counselors and therapists. So this is the methodology and system architecture. First, we get the videos and images. Let's just talk on the videos. And then we pass them through the API layer. That is to give access to, okay, that's the gateway in that we are giving access to the therapist, let's say to a given session, and yes, to a given session. Then the security and compliance layer, does it comply with ethical, let's say guidelines? Is there data privacy? Yes. And then we move to the processing layer. That is where our vision transformers are. We are passing the videos through this block, or we extract the frames, we process the videos, let's say the images, we resize them, and then we map them to a given set of emotions, to clinical states, and then to therapeutic interventions. And then when we come up with everything, we store the data in our given database, and then also the client, the therapist, is able to know what is going on. I already talked about it. This is the maybe I just the vision transformer equations, the patch embedding and the position embedding. First, we are going to break the images. Let me just patch embedding. We are going to break the images into tiny patches, and then these patches, we are going to send them to the transformer blocks, which is the attention layer normalization. That is for normalization. And then the first summary, which we are going to extract the tokens, that is under the CLS, and then the classification, we're going to classify them according to the given sets of emotions we have. And then the confidence meter, we are going to rate them according to the confidence scores that we have. And then the top emotions, we have anger, fear, sadness, happiness. You can see that's the top K emotion, which is anger. The success, we are going to rate it. And then the intervention, when we rate, let's say the anger, we rate it, the success, we rate it, and then map it to a given clinical state. And then after the clinical state, a therapeutic intervention. And then after the therapeutic intervention, let's say we validate the message, we validate the feelings in that we have come up with this suggestion. Why? Because the client disengagement is increasing due to, let's say, a lowered gaze. Yes, that's why we have our output, and our output is stored in a JSON file. So let's see. We just talk about this. The data sets we use, we combine this FER 2013 and some web images. The samples we used were over 9,400 labeled images. We classified the emotions into 7 groups: anger, disgust, fear, happiness, neutral, sadness, and surprise. We split them into 70, 15, and 15 percentages. Then the image size is 80 by 80 pixels. The data sets we used, there are, for the knowledge graphs, they were divided into 3 groups. That's emotion to be, we are mapping the emotions and the behaviors. We're mapping clinical correlations to the emotions, and then the therapeutic interventions to the clinical states. For the emotion behavior relationship, we are linking 6 basic emotions to 20 specific behaviors. And then for clinical correlations datasets, we are linking the basic emotions, the 7 basic emotions, to 11 clinical states, the clinical states like frustration, anxiety, grief. And then For the therapeutic interventions, we are linking the 4 clinical states, only 4: anxiety, depression, frustration, engagement, to 10 therapeutic interventions. For example, cognitive restructuring, behavioral activation with modalities like CBT, DBT, yes, and that. So this is showing the training set distribution, the number of images we use for each emotion. This is the image size. I said we resize the images to 80 by 80 pixels, making the aspect ratio to be 1. The behaviors by emotion, that is, we are mapping the given set of emotions to anger out of, let's say, um, four behaviors. All of them were mapped correctly to anger. Yes, to anger. We listed down a given set of images according to the different behaviors and then map them to the given emotions. The clinical correlation strength, we are mapping the emotions to the clinical states. We find that there is the evidence levels is between moderate and strong, making the system really a good one. Then the fine-tuning performance. Here we find that happiness has the highest score compared to anger, because happiness, it is very easy to detect happiness in a person due to the facial movements, which are easy to detect. But for anger, yeah, anger can be easily confused with sadness and with disgust. That's why it has the lowest score and the lowest recall and support. Yes, this is the confusion matrix. Diagonally, we have the true positives. We find that happiness is still having the highest score. And then the confusion matrix for happiness with fear is only 1. Like, one of the images was confused, but fear, and then for the false negative, I mean false positive, there was only one image which was confused with fear. But then for the true negative, yes, only 0. Like, none of the images was confused with fear. Okay, let me talk about the justification, why we chose the knowledge graph large vision language model. Scientifically, we chose it because it moves beyond just spotting behaviors to understanding their clinical meaning. Other models might see a client, look away, and let's say most of the therapy sessions happening right now, the therapists ignore these micro expressions, which is not really good, because when a client comes to see you and then you ignore these things, the session will not go on successfully. So that is why we chose the knowledge graph large vision model, because it will give us cues to figure out the client, or why the client is anxious, or um, it actually just gives us the reason why something is happening. Yes. So the technical justification, a system's technical strength is a hybrid design. It uses clip to get the visual cues from the videos, and these cues are structured into a knowledge graph, therapy concepts, then a graph neural network, then reasons over these graphs connecting the observed behaviors like fidgeting to probable clinical states like anxiety. Crucially, this process is explainable. That is why we can show the therapist the exact chain of reasoning the model used to reach its conclusion, and this builds trust in the AI's feedback. We have already deployed this system on Render, and every time we make any corrections, we push them to GitHub, then the app is updated automatically with the latest changes. And this is just a brief demonstration of our project. I already say that it detects the non-verbal cues, the micro expressions, which contain the client's true internal emotional state, and then these observations are mapped to a therapy-specific knowledge graph that encodes established clinical relationships, enabling the model to reason beyond mere behavior recognition to infer underlying clinical states such as disengagement, and suggest context-aware therapeutic interventions. The system provides therapists with explainable feedback on a tablet interface, highlighting behavioral evidence and confidence scores to enhance situational awareness without disrupting the therapeutic alliance. So some of the limitations, we majorly focus on micro-expressions, leaving out the body posture, voice, tone, and gaze. But the solution we have is that we are going to integrate the body postures, gaze, and voice tones data such that we can consider all the human body and its actions to know the exact emotion of the person. Another limitation we have is that the model developed is computationally intensive, creating a potential lag for real-time feedback. We're going to use a more aggressive quantization, that is int8, and dedicated neural processing unit optimizations to improve inference speed. The conclusions, the system successfully detects and gives real-time feedback on non-verbal cues according to our tests so far, and it's 90% accurate. However, the performance of the model decreases with input of low quality data. So the future works, and we are going to integrate deep learning to improve the accuracy of the model, and then more research to address scalability using larger data sets. In conclusion, we have to appreciate our supervisor, Mr. Gali Wango Marvin. You have really been a great help to us. Words cannot express how grateful we are. And yes, we have learned a lot in this course. With you. You have been a great mentor and a great help to us. Yeah, thank you all for listening to this video.